Good morning and good afternoon, and welcome to this presentation on Newton's second law. And the intent of these presentations are for STEM classes in the 6th grade who are trying to get a handle on Newton's laws. And hopefully, if you're watching this video, you have watched the introduction and video 1 to gain a further understanding. And I don't believe I have any other reference videos in this one, but on the other videos, hopefully you're able to find those corresponding videos that I have in my slides and able to watch those or something equivocal. All right, so let's talk about force today. And think about what force means, okay? If I were to place a ball on a table, all right, what forces would be acting on that ball? Well, if you're saying, well, there's the force of gravity, you're absolutely right, because that gravity is constantly pulling, right? And that table is getting in the way of that ball being pulled any more towards, well, the center of the earth. Now, if I were to remove the table, all right, that ball would fall until it hit the ground. And if I dug a hole, it would go until it got to the next part. You get the idea, right? So here's the thing. There are different forces at play at any given time, okay? Now, Newton's second law says the acceleration of an object is directly proportional to the force applied and inversely proportional to its mass. Now, if you're thinking, Mr. Cadle, this is for the 6th grade, I don't understand what that means. Well, here we go. Let's take a look at this in a different perspective here. All right, force equals mass times acceleration. Force equals mass times acceleration. All right, that's the easiest way to understand what that concept and that I just said means. All right, now specifically with acceleration is the change at which the force happens. All right, so let's go back to that ball. Let's place that ball at the middle of a table and then gently tilt the table in one direction. You'll notice that that ball starts to move slowly, then get faster and faster and faster until it falls off the edge, right? If it's at a gentle slope. If it's at a severe slope, then it falls pretty quickly, right? So what you're seeing is acceleration. In other words, you have force, the gravitational force, right, working on the ball itself, depending on what the ball is. If it's a ping pong ball, it's super light in mass. If it's, say, a bowling ball, there's a whole lot more mass there, right? And then you have changes. Acceleration is changes in meters per second or changes in feet per second, all right? In other words, forces can cause acceleration. If you don't know what acceleration is, I'm sure most of us have ridden an automobile. You get to a stoplight, and the speed limit is 35. The stoplight goes from red to green. We accelerate until 30 miles an hour. Does that mean you hit 30 miles instantaneously? No. All right, it takes time for the vehicles to get there. Some a little bit faster than others, right? So measurements are usually done in, well, newtons. Why newtons? Because, hello, Sir Isaac Newton. We've been talking about that dude, right? And so newtons is the force measurement that was traditionally used. Now, if you're using or measuring something in newtons, you got to use kilograms and meters. In other words, you got to use the metric system. Now, if you're in the U.S. and you want to calculate something according to the imperial system, you use pound force. All right, pound force is something like newtons, but it's a little bit different. All right, I say it's different. It's measured a little bit differently. All right, we measure pound force by pounds by changes in feet per second. All right, now here's the deal. More mass requires more force for the same amount of acceleration. So go back to that shopping cart. All right, that shopping cart, when it's light, is super easy to push and get up to walking speed. That heavier shopping cart with more items in there, a lot heavier, more resistant to change, a little bit more force is required to get that to walking speed, right? Now, here's the thing. If mass stays constant, right, if the mass stays constant, more force equals more acceleration. Less force equals less acceleration. Pretty simple. So let's say, let's do the shopping cart, right? Let's say you have a younger brother or sibling, right? A younger brother or sister. And they're like, say, like 3 years old, and they try to push that big, heavy shopping cart, right? Well, they have less force they're going to apply, so it's going to be tougher for them to push that heavy, full shopping cart. Whereas you, or maybe your older brother or sister, can do it with a little bit more ease, right? Why? Because, well, there's less force being applied, and then more force being applied by the larger, stronger individuals. Now, if force stays constant, right, less or more mass equals less acceleration, less mass equals more acceleration, all right? So, if I drop a ping pong ball and a ping pong ball sized object that weighed 10 pounds, all right, one is going to accelerate faster than the other one will accelerate, all right? So until they both reach their own terminal velocity, but that's a discussion for another day. Big takeaways: more force, more acceleration. Less force, less acceleration. That's if the mass stays constant. If the force stays constant, more mass, less acceleration. Less mass, well, there you go. All right? So again, pushing shopping carts, throwing different weighted balls. Has anybody ever tried shot put? Shot put's crazy. You basically put a big ball inside, and it's about the size of a softball, right? But it's made out of metal, almost like iron, right? And you have to kind of push it out. There is nobody who's going to throw one of these big, heavy shot puts by doing the traditional throw like you would a softball. All right. Why? Different weight. Okay. Softball much lighter. Okay. You can throw it a little bit easier. Shot put much heavier. You got to keep it closer to your body to keep. And if you try to even throw on that thing, you're going to break something and you're going to hurt yourself. All right. You also have acceleration of vehicles. All right. Why is it that big semi-tractor trailers take more force and more power to get up to speed, and it's tough for them to get there at, say, like that 35 miles an hour, right? If you pull up next to a semi-tractor trailer and you're in a car and you're both accelerating to 35 miles an hour, chances are your car is going to get there faster. Why? Even though it has less power, it's going to be lighter, right? So again, different weights of the vehicles at play. Or even riding bicycles uphill, right? Why? Because that slope is creating more resistance, more force. Alrighty? So those are some things to think about there. Now, if you're in class with me, we're going to do a quick in-class demonstration. And I'm going to explain that to you guys here in a few moments, but I'm basically going to have two relatively equal objects, right? Equal in the matter of how they're designed, but they're going to be weighted differently. And I'm going to put them on a slope, and we're going to see how they react differently. Alrighty? And additionally, if you are in my class, make sure we take care of Activity 3. Activity 3 will ask us to solve a little bit of math, but it's easy math, and it uses the metric system. So we don't have to worry about converting newtons to pounds. Alrighty? So there you go, ladies and gentlemen. Super short and sweet video on force.